Okay, well, good morning, and thank you for coming out to IMSA's Institute Day for 2022. I hope that you find some interesting sessions. I'll be doing 3 today, all in the elementary field. My name is Patrick Young. Let me throw on my slideshow here. All right, and at any time, if there is some technical difficulty going on, and I'm not responding, feel free to unmute yourself and holler out. We have just a handful of people here, so that would be no problem at all to ask questions at any time. You can do it in chat, but also don't mind popping onto audio. Okay, well, our presentation today is Einstein for 3rd grade. And I call this 3rd grade because I'm particularly addressing some 3rd grade standards in mathematics and science, but the general principles and indeed the activities that I'm going to share with you could certainly be done at other grade levels as well. Note my email here. If you have questions at any time, you can shoot me an email. If you decide to try out any of these activities, I'd love to hear some feedback to know how it went in your particular classroom. So feel free to send me any comments there. You can also download both a version of this slideshow as well as the curriculum associated with it at the IMSA Digital Commons, and links for all that are available in that web page that led you here. Okay, here's our agenda today. First, we're going to talk a little bit about Albert Einstein, but we're not going to talk about that gray-haired physicist that you may be more familiar with. Instead, I'm going to focus on his younger days, and in particular, his youth, his experiences as a student, the formative experiences that he went through, and later on in life, what his thoughts about education are. And he had quite a bit to say on that particular topic. The next thing I'm going to do is show you a book that you can read with students in your classroom called On a Beam of Light. It's a wonderful book, and I'll be paging through that a little bit with you today. After that, we're going to look at Einstein's thoughts on teaching. We're just going to pick a few of his comments and think what that might mean for our practice and our classroom. Then I'm going to share with you 4 different activities. These are all hands-on activities, simple things that you can do in your classroom that relate to force and motion, and these address NGSS standards for physical science. There's also a bit of grade appropriate math there as well. And finally, we'll talk about creating an Einstein Center in your classroom, inspired by the environment that he grew up in. What type of things could you have available in the classroom for students to interact with that might give them interesting experiences to ignite their imagination and their sense of wonder about the natural world? So this is what we're going to do in the next hour. I'm just going to go kind of a timeline here. Einstein was born in 1879 in Germany. He grew up in a home that doubled as the workplace of his father and his uncle, who were engineers. They had an electrical workshop, and they were prototyping equipment for sale. It was never a particularly successful business, but it did provide a very rich environment for Einstein. That was his playground because he didn't spend a lot of time running around outside with other kids. He was very quiet and withdrawn as a youth, so he did spend a lot of time in the workshop. Now, the work that his father and uncle were engaged in was electrification. This was an age of technological revolution. Electricity was being brought to the public for the first time. It was being used for telegraphs, but the number one and first use of electricity for any town that could afford it was street lighting. So producing the equipment that made this available is what was going on in that Einstein laboratory. Albert was constantly surrounded by magnets, electricity, and rotating machinery. Probably not the safest environment for a kid to play in by today's reckoning, but it certainly provided a lot for him to see. Now, his uncles and his father did not provide a lot of explanations for how these things worked. It was a mystery to him. And that's important. That's important to the way he thought about the world, because he was all about thinking about what was mysterious. Throw some thoughts in the chat. Does anybody know what they're looking at here? Can you identify any of those machines or even take a guess? What do you think we're looking at here? You see a lot of things that look like wheels, hand cranks. These are basically machines for, you put in some type of mechanical motion to make something turn. And what you're actually turning there are magnets. And when you turn magnets that are surrounded by coils of wire, this produces electricity. These are very primitive electrical generators, what they called magnetos at the time, because they all used magnets. All right, here he is. He's 5 years old here. Now, his parents were very worried about him because even at the age of 2, he hadn't spoken a word. And even at 5, he was almost completely nonverbal. He could speak. He just very seldom was willing to. At the age of 5, Einstein recalls in his later writings that he was ill for a while and confined to his bed. And he recalls his father giving him a present. And that present was a magnetic compass. And Albert was fascinated with it. No matter how he turned it, that needle would always point in one direction. And he marveled at the way that behavior implied some type of invisible world, something that applied force that he couldn't see. And he never forgot that feeling of wanting to discover how it is that this mysterious invisible thing works. That kind of thinking would drive him throughout his career. As with all the other machinery, his father would not have provided an explanation for what was going on there. He left it as a mystery. So here's a question for you. And not a right or wrong answer here. This is just to stimulate your thinking. Feel free to throw out any thoughts you may have in chat. What is more valuable for a student? The emotional draw of a mystery, or actually getting to the answer? As teachers who typically have the answers already in our pocket, we tend to focus on those. And sometimes I think it's not to the advantage of our students to forget about that emotional draw. I would suggest, yeah, that's exactly right. Some kids absolutely want the right answer no matter what. And that's good. That's wonderful. Help them find the right answer rather than giving it to them. That's what I would suggest when possible. Of course, all students are different. So what works best for one, not necessarily going to work for the other, but keep that in mind, that power of emotion. And we'll come back to that later when we're talking about what Einstein said about education later in life. So the next present he got was a violin, which he was not excited about, and he did not like playing it particularly. But he did for the same reason many young people do when they're given an instrument in elementary school. He wanted to make his mom happy, so he played it. Now, eventually, after about 5 years of playing it, he discovered Mozart, began to see the mathematical patterns in music, and he came to absolutely love it. And later in life, as an adult, there were two things that he loved above all else to do in his leisure time. One was to play the violin, and the other was to sail. He usually lived near a lake, and he would rent small sailboats and go out on the water. Okay, from the very first, Einstein's teachers did not consider him to be a good student. Aside from the fact that he was nonverbal, he was inattentive, distracted by his own thoughts, and he was very loath to focus on what the teachers considered to be important. His only interest was to basically pursue what was going on in his own mind. He was skeptical of authority, and he despised the type of discipline that was expected in German schools of that era. Independent thinking was absolutely not encouraged. And in 1889, he graduated from elementary school to the next school, which in German they would call the Gymnasium. Here's one of his quotes from later in life. The teachers in elementary school appeared to me as sergeants. Einstein despised the military, so that was about as rough a comment as he could come up with. But he was in particular speaking about their sense of discipline. So here's another question for you to think about. How might being skeptical of authority be advantageous for a career in science? Being skeptical of authority is something that Einstein was throughout life. Yeah, it might encourage you to look for new answers. There is always a community out there that has, the current thinking established. And if you're the type of person who is hesitant to confront conventional thinking, hesitant to question things, then what chance do you have of really making any breakthroughs? So this aspect of his personality, while it certainly made education difficult for him, was also very important to his being able to revolutionize the study of physics and overturn the way scientists looked at the world. Yes. Okay. Gymnasium did not go any better than elementary school did. Einstein loved to learn, but he hated school. He learned best from reading books on topics of his own choice and by his own very active imagination. Now, his fluency finally bloomed, but of course that only led to more conflict with his teachers. They found him disruptive. He questioned them and did it in front of the rest of the class. He was expelled from school at the age of 15, which is 3 full years prior to graduating high school. And here's one of his comments from a teacher who'll never make a success of anything. So that was it for his formal education at this point. He viewed the oppressive education system as a byproduct of German militarism, which he despised with a passion. Einstein was, throughout his entire life, even from a young age, a humanitarian and a pacifist. And in 1896, he actually renounced his German citizenship. So at the age of 16, he was a high school dropout without a country. Now, he aspired to be a physicist, and around this time, he was starting to record his own ideas about space and about magnetism, and he would send those to learned people he knew, particularly his uncle. He couldn't get into a university physics program. There was, however, a school in Switzerland, the Swiss Polytechnic, where he could get in by taking an entrance exam. So he tried that. He failed his first entrance exam, but he spent a year studying and was able to get in on his second try. Here's another question for you. With what college degree did Einstein graduate? What was his undergraduate degree in? Take a guess. You're right, it was not physics. He couldn't get into the physics program. That exam let him get into a different program, a program that had fewer prerequisites, and it was education. He graduated with what was essentially a bachelor's in education. He was an ed major. His degree would allow him to teach science and mathematics at the high school level. He never did get the chance to do that, though. He couldn't get a job because he couldn't get a letter of recommendation. So he took a job as a third-class patent clerk in the Swiss Patent Office. And that's where we're going to leave our history of Einstein for now. That was basically to help you understand where he's coming from. You don't need to share that with students if you don't want. You can. And I would highly encourage you to check out this book, though, called On a Beam of Light. And if you just wanted to show it on YouTube, there's at least one recording of somebody reading it. But let's take a look at it now. I need to switch up my camera view here. And when I am second. All right, for some reason my monitor's not working here, but you're seeing the book On a Beam of Light here. Is that correct? Can somebody give me some feedback in the chat
Yes.
here? Thank you, appreciate that. Okay. You could use this book in various different ways. It starts at the very beginning with him being born. I think the artwork is kind of nice in this primitive way. It's easily, something that your students could read. And I would probably go through this up until here, where Einstein's father is giving him the gift of the magnetic compass. That would be a good place to pause and then go into the hands-on activities, because the first activity I'm going to show you today actually starts with doing experiments with a magnetic compass to figure out what it's doing. Okay, let me shift back cameras. Let me get back to my PowerPoint. There we go. Okay, what I'm going to do now is go through some of the things that Einstein said about education, and just to stimulate our thinking a little bit. It is the supreme art of the teacher to awaken joy and creative expression and knowledge. Think about that for a moment. What does that mean to you? What would that mean to your practice in the classroom? Here's what impresses me about it. This is my emphasis, not him, but he's awakening the joy. Yes, there is knowledge there involved. There's creative expression, but he's saying here that the supreme art of the teacher, the primary job of a teacher, is to awaken joy, something very much emotional based rather than facts and figures. I'm sorry, Karen, I'm just now seeing your comment. Is everybody able to see the yeah, hang on just a second. Okay, there we go. Okay, here's our next one. Oh, you gotta love that suit. Gotta love that suit. Three-piece plaid. The most valuable thing a teacher can impart to children is not knowledge and understanding per se, but a longing for knowledge and understanding. Here again, he mentions knowledge and understanding a couple times, but what's the most important thing to impart? It's that longing. Again, it's the emotion that precedes and is a prerequisite for, in Einstein's view, authentic learning. But how do you inspire longing to learn in students. Of course, that's a tough thing. In Einstein's view, here's another quote that would give us a hint. The most beautiful thing we can experience is the mysterious. Maybe it's that mystery that we need to provide. These two pictures both show Einstein out on the water. He did spend a lot of time sailing. You'd always have a notebook out there with him too. Here's a very famous quote: "Imagination is more important than knowledge." He's not trying to put down the importance of knowledge. Obviously for an academic, knowledge is the end goal of everything. But in order to get there, you have to start with the imagination. And I think that's what he was getting at for the most part with this statement. This is a quote about physics, but I think it applies to science as a whole. In the matter of physics, the first lessons should contain nothing but what is experimental and interesting to see. And one of the important words to highlight here, I couldn't narrow it down to one, but certainly interesting. Got to catch students' interest in something and be experimental. So we're starting out, we're hands-on, we're playing with things that help us fire our imagination and desire to understand how the universe works. It is nothing short of a miracle that modern methods of instruction have not yet entirely strangled the holy curiosity of inquiry. For this delicate little plant, aside from stimulation, stands mainly in need of freedom. There's a lot to digest there. He was being critical of the educational methods of the day, and there is still a lot of traditional instruction in that mode. What he's saying, in my view, is that inquiry is what we're after, the desire to understand and figure out how things work. And inquiry really only needs two things: stimulation and freedom. Think about that when you're getting ready to do some type of activity with your students. Okay. So what we're going to do now is take a look at 4 different activities for your classroom. And these are available to you. If you go to the IMSA Digital Commons, you can download these in PDF form. There's fairly simple materials required for these, and feel free to ask questions or shoot me an email if you're struggling to find things that that will work for you. All of these activities involve things like electricity and magnets, and yet what we're really after here, what the NGSF standards are that we're examining, are really about how forces interact with motion and stability. And although I give you a particular procedure to follow, you will notice as we go through here that there are multiple opportunities for students to go off and do an investigation of their own choosing that occurs to them in the course of this activity. And that's the activity, that's what you really want students to be doing. So you're going to need some magnets. Black ceramic magnets are actually getting rather hard to find these days, but these powerful refrigerator magnets are wonderful tools. In fact, in some cases, they're a little too strong. It can be hard if you get a stack of them for students to pull them apart. What I do is I take each of these refrigerator button magnets and I glue it down on a wooden disc. You can buy these on Amazon. They're very cheap. I just use Elmer's glue. Something like super glue might work even better. I haven't really tried it, but Elmer's works good enough. And that makes them much, much easier to work with. The first activity is going to involve magnets and compasses. You're going to start with a single compass and a single magnet, and students will play around with how one affects the other. They'll come up with some questions. They'll be encouraged to propose experiments. Once they're done doing whatever experiments they like to do, then you can move on to what's pictured here, which is to see how close do I have to get this magnet before the compass actually responds to it. In other words, how far does this magnetic force reach? The actual truth is it reaches out for an infinite distance, but that compass is not a perfect instrument, not a perfect tool, so it probably won't notice the magnet until you get within a few inches. But then students can play around with, well, what if I flip that magnet upside down or bring it in sideways? Again, they'll come up with their own questions, and every time they have a question, ask if somebody in the class can provide an idea that might explain it. And then you go into, well, how can we use these tools to test that idea? Now, if you're letting students do all of their own experiments, what if you don't have time to finish the one that's written here? Well, then don't. Focus on the ideas that the students come up with. Whatever they learn in investigating their own ideas is going to be more valuable than what they learn using this prepared idea that I'm showing you now. It's their questions that matter most. Activity 2 lets them play a little game. We provide them a little, like a race course, and they'll put a magnet down on that course, and they'll use another magnet, which will repel the first, and they will try to push it around that track. So it'll look something like this. One magnet represents the sailboat, the other one represents the winds, and they're, without actually physically touching one magnet to the other, just using the force involved, they try to complete a circuit. And of course, they'll start making observations about forces and directions and motion, and hopefully they will come up with some neat questions and tangents that they want to run off on. If you have competitive students in the classroom, some are going to want races, and that can be fun too. The next game they're going to play is magnet ball, which is, I guess, kind of like soccer. There's going to be one ball out, a magnet out there, which we will call the ball, and two players, each will have a magnet representing their player, and they're going to push their player around on the field using popsicle sticks or, craft sticks. And of course, all of these magnets, if you've assembled them correctly, are going to be repelling each other. So the idea is to push the magnet representing the ball through the opponent's goalpost. So now we have a magnet that's responding to multiple forces. And they can see the way forces add together to produce motion. Activity 3 is about cause and effect. It may seem obvious to many adults by the time you're old enough to bother thinking about such things that effects are always preceded by a cause. It's actually something that takes some time to develop in people. You probably don't have any recollection of your own development of it. But if you probe students' understanding of this, you can find quite a variety of stages of development that they might be in. So this activity is going to help further them toward an appreciation of the relationship between cause and effect. And what you do is you lay down a strip of aluminum foil and you put that compass on it, and you want the needles to be pointing toward the ends of the foil. And it's fun when that doesn't happen right away. You'll watch the students try and turn that compass to make it line up. Well, that won't work because the compass needle is not going to rotate with the round base. They're going to have to rotate the aluminum foil beneath it to get that aligned with the compass needle. Then you're going to bring a D-cell battery there, and you're going to bring the ends of that foil up and touch it to the battery. That compass is going to react. Why? There's no magnets in this picture. Why would it do that? That's something students are going to be interested in, and they can come up with all sorts of ideas for why it might be happening. And they will come up with ideas to test. So that's what this activity is about. Now, in the handout that you download, I do give a little bit of background information just for your interest. Anytime you have electricity flowing through something, that electricity creates around itself a magnetic field. Do students need to know that? I don't think so. Not in third grade. But I think it's important that they see mysterious things like this happen and try and figure out what's going on. Activity 4, this one has been around for a long time. It's building an electromagnet. If you take a wire and coil it around a nail or a bolt or any type of metal cylinder and pass an electrical current through it, you will create a magnetic field within that coil. Having a piece of metal in there just makes it stronger. It would work even without the nail. And then we're going to let students pick up small objects like staples or paper clips and move them from one place to another and puzzle what's going on here. Why is this thing magnetic? Why is it able to lift items? How can I construct this thing in different ways that would make it better at picking things up? So here we're throwing an engineering challenge at them. How many paper clips or how many staples can you actually pick up? What different things can you change to do that? So that's what the activities are. And I'm actually going to show you the materials in a moment, kind of go through on my tabletop how that works for you. But before I do that, I do want to talk again about the idea of an Einstein Center in the classroom. Now, the purpose of this whole thing is not to turn your students into an army of little Einsteins. That's not going to happen, and the world doesn't need that, really. They don't need that. Einstein was a very unique individual, and all of your students are themselves very unique individuals. But you certainly want to provide them for opportunities for interacting with hands-on items of a variety of types to see what sparks their imagination. And here is something that you can put together to help students explore physics. Magnets, compass, paper clips, all these different items involving electricity, light, magnetism, force. All these are the types of things that will help them explore the things that Einstein studied. And how you want to run your center is up to you. I know conventional wisdom and research is it has to be very purposeful. They should have a procedure to follow. And you can, in fact, give them the 4 activities that I just showed you and say, okay, there's what you do in your center. Or you could be more freeform about it. Which is actually what I would recommend here. The instructions can be as simple as, oh, I don't want to say play with this stuff, but how about this? Make something interesting happen with these materials. What is interesting? Well, that's up to a student. Typically, when they see something change in a way they don't expect, that's usually interesting. Then you wonder how or why it happens. And then you test your idea by experimenting some more. Now, if you'd like to bring writing into this, I've also prepared for you a sheet here that kind of guides them through the process that I just mentioned. Make something happen with magnets, a battery, or a light. That's their instruction, and then a writing prompt. I saw this happen. Now, of course, writing is a continuum all the way from pictures through paragraphs. So, depending upon where you students are and what you want to emphasize, you could either ask for complete sentences or not, wherever they are, whatever it is that you're currently working on. So the next step, after they see something happen, how and why did it happen? This is what I think. They make some guess to record there. And then they come up with an experiment. If my idea is right, I can test it by doing this. Now, this is the toughest spot to make a student record because they want to jump right into doing the experiment. And that's okay if they do. And finally, the last box there, here's what happens when I experimented. And hopefully that might lead to even more questions for them to explore. All right. I am going to shift camera views again. Okay. Are you seeing the sailboat racing sheet again in my hand?
Yes.
Excellent, thank you. Okay, let's see. The first activity was, well, we just need, I'll just use a blank piece of paper here, is to take a compass. And here are our magnets. I've got them stacked here. When you glue them down, oops, that's the wrong size. When you glue them down to these little discs of wood, they repel each other. You just have to be careful when you glue them down to make sure that they all have the same side up. Every magnet has a north face and a south face, and they're not labeled, and it doesn't matter which is up and which is down as long as they're all made the same. But for this activity, they're just bringing, first they're examining all the crazy things a compass will do when you get a magnet near it. But they'll notice they can move the magnet far away and it doesn't affect the compass. Well, how close do you have to get? You may have rulers like this in your classroom that have a strip of metal along the edge. Those can interfere with what's going on here, that strip of metal. So if you can, try and get rulers that don't have any metal in them. And I'm going to set this up so the needle here is pointing toward 0 inches. One of our math standards in 3rd grade involves measuring things to a 1/4 inch. And then the question is, as I slowly move this closer, how close do I have to get before I see a reaction in the compass? So that's what this activity is all about. Encourage your students when they think they have an answer to compare the results with other groups. There will be differences. Why is one group getting a different answer from another? Those are wonderful questions that can lead to experiments for them to conduct to try and find the answer to that question. So that's the first activity. Our next one, our sailboat race. We can, there's a little line here. It's kind of the start line. And I'll take another one here. And this one I'm going to move with my hand. And the goal here is to push this along, keeping it on the track. Of course, it's a nice straight line when you're going with the wind. You're going against the wind. That sailboat's going to have to zigzag back and forth. They call that tacking. Oh. And students will probably want to come up with some type of penalty. What happens if you go off the line? When I first did this, I came to a spot on this track where the magnet was kind of sticky. Didn't want to go. And I rubbed the paper. Gee, is there some spot here? Is something wrong here? No, the paper is perfectly smooth. What I didn't realize is underneath on the table, there's a big metal bracket holding the legs on. So that was an interesting discrepant event. Something I didn't expect was happening. I had to figure out what was going on, and that was a lot of fun. So I had to put it up on this box here to keep it a little bit further from the table so it would work. So that's your sailboat racing. Here's your court for magnet ball. I took one magnet and I just, with a Sharpie, I put some marks on it so we know, okay, that's the ball. Now this is a game for 2 players. They each start with their player outside of that center ring. And each player has a popsicle stick. Now, I'm allowed to move my player with this stick. I'm not allowed to touch the ball. I'm not allowed to touch the other player. I'm not allowed to touch the other guy's stick. What I am allowed to do is this. And of course, what I'm trying to do is get it past the defender and into the goal over here. Now, exactly what do you have to do to score a goal? What happens when you're out of bounds? These are all good questions. Let your students figure out the rules for this. Let them come up with their own game to play out of this. So here they're going to confront the observation that when a magnet is experiencing force from directions like this, it's not going to move in the direction of either one of these forces, but in a direction somewhere directly in between the 2 forces. They take high school physics, they'll learn about vector addition. Here it's just an interesting phenomenon to observe and to think about. Let's see. Experiment 3, cause and effect. We're going to take this strip of aluminum foil and we're going to put a compass on it. And we want our aluminum foil, let me get these magnets away from the compass. We want the aluminum foil to be lying parallel with the compass needle. It does take some patience here. These are cheapy compasses, so it takes it a minute to settle out. Okay, there we go. So I know you may have trouble seeing that, but the needle is pointing along the aluminum foil here. I take a D-cell battery. This battery is 1.5 volts. All of these things work dramatically better if you use like a 9-volt battery, but don't do it. Students can get into trouble with 9-volt batteries. They won't get into any trouble with this. Okay. And if I bend the edges of this up to touch the battery, and again, I'm sorry, from this view, you probably can't see it very well. Open and closed. The needle reacts. Why would a needle react to electricity flowing through the foil under it? That's something for them to think about. come up with possible explanations, and those possible explanations are things to do further experiments about. And the last activity is the electromagnet here. And here's a battery. Here I've taken some wire and wrapped it around a nail. And you want students to work in groups. Sometimes extra hands can help here. And when I attach these ends to the battery, electric current will flow through here and a magnetic field will form around the nail. And what you can do is you can give them staples or a nail, and they can put here in pile A, and they're going to try and pick it up here and drop it in pile B. And of course, there are actual machines, cranes at scrap yards and recycling centers that actually use this exact technology to move things. Paper clips, you get the smallest ones you can find because you're probably not going to pick up more than one with this battery. Staples, you could are lighter, and obviously you can pick up more of those. And then let students experiment. What if I use a longer wire and put more lines on here? What if I put 2 rows of turns on here instead of a single row? What if I try it without the nail in there? What if I try it around my pencil? That will actually work because the graphite in the pencil does have some useful properties in there for a magnetic field. So you can also, if you have battery holders or more holders, you can try putting a couple of these batteries together. That's fine. That's 3 volts. That's not going to cause any trouble. If you get much more than 3 volts, though, these wires are going to start getting hot. If you use a 9-volt battery, and even the battery itself can start getting hot, and that can cause a dramatic failure of the battery. So I'd steer clear of 9-volt batteries at this level if I were you. Other things that you can experiment with, if you have around your classroom, if you're making your Einstein Center, get little flashlights. This one's too expensive to give the students. You can find cheaper ones in places like Oriental Trading. Little mirrors at craft stores. You can get little plastic reflective segments. Well, there's all sorts of things. Use your imagination. Put together a diverse set of equipment for students to do experiments with. That's basically what it's all about. Okay. So that's basically what I had for you today. What questions do you have? Questions or comments? And feel free to unmute yourself. We've got a nice small group here. We can chat. What occurs to you as you watch this? Undoubtedly, you've been thinking about, well, how will this look in my classroom with my students? Tell me your thoughts. Feel free to share.
I have a lot of competitive kids, so I think that they would really like that one with the boat with the track. I think I can see them really getting into that, and the game with the popsicle sticks.
Yeah. Not everybody, but most people are motivated by competition and have fun with it. Keep a keen eye out, though. You will have students who absolutely do not. And rather than have them just shrink back and stand back from the group that's playing, if you can get those kids together in a group, they'll go ahead and compete, but they'll feel less threatened when they're not surrounded by other kids who are really charged up about it. So good thoughts. Other thoughts, observations, or questions? Okay, well, I want to thank you for spending some time with me today. Again, download the materials from the IMSA Digital Commons and take a look. I go into a lot more detail about everything regarding the activities there. Not because you have to be detailed and structured about it, but it will help you think through it as you read it, and then feel free to adapt and modify for your classroom needs as you like. When you're done here, the next thing I'd like you to do is to go back to the web page that you came here from. And I think I can probably show you that here if I share my screen again. I want to show you there are two evaluation links to look at. Over here on the right, there is an ISBE evaluation form and an IMSA evaluation link. If you would, over the next 5 minutes or so, fill both of those out, I would really appreciate that. And other than that, I will let you go, and I hope you enjoy the rest of your day.